Good afternoon, everyone. I hope all of you have had a great lunch, but don't doze off yet because we are going to have a very wonderful and exciting session by some of our professors who are going to be talking about their research that they are doing in IIT Bombay. Firstly, I would like to invite Thakur. He is an assistant professor in the Department of Computer Science and Engineering in IIT Bombay. His research interests include program analysis, computer optimizations, compiler-driven optimizations, programming languages, software engineering, and parallelization. Prior to taking an appointment at IITB, he was at IIT Mandi for more than 3 years, wherein he was bestowed with prestigious Teaching Honor Roll Award in 2021, and his research group is named as COMPL, if you want to join. Manas holds his PhD and Master's degree in CSE from IIT Madras, and his thesis supervised by Professor B. Krishna, titled Precise and Efficient Analysis of Java Programs, won one of the Institute Research Awards and jointly the IBM Best Thesis Award in 2019-20. Prior to this, he obtained a BE in Computer Technology from KITS Ramtech, securing 4th rank across several institutes, affiliated to RTM Thakur University. He hails from the beautiful town of Balaghat, situated in Madhya Pradesh, India, and claims, if not computer science, he would have been a historian. And he also writes poetry and articles, technical and otherwise, teaches yoga and likes traveling. And to know more, please follow his blog, Star Winner. I hope you get the headquarter reference. Let's hear from Master regarding compiling code just in time.
How many of you, so I am also supposed to wake you up after lunch, right? So how many of you program? How many of you write programs? Everybody, I hope. Okay. So how many of you compile programs? Okay. Some people are asking compile interpreter, I don't know, but okay. Fine, most of us. So it's good to see programs were the ones that introduced you to computers in some sense, right? They allowed you to play with them. And compilers are again a software that all of us use. So it's better to know more about programs in some sense, and that's what is this research area, the whole work on compilers and programming languages that he mentioned about, right? So, well, we'll be talking about compiling code just in time, and to begin with, we'll be talking about super fast Java. Now, how many of you know Java? Very good. How many of you know Java to be a super fast programming language? Okay, at least 3-4 hands I can see. So that's the first thing that comes to your mind, right? Wait, what? Super fast Java? I heard about super fast C. I heard about super slow Python, but I never heard about super fast Java, isn't it? So let me just show you how fast Java can be with a demo to begin with. What I have here is a C program, a C++ program and a Java program. All of them are supposed to do the same thing, some trivial computation. We don't care about what is happening. What I would like to point you out to is that there are two fields, n and res. N is taken as a command line argument, and there are 3 nested loops, all of them run from 0 until n. So basically, how long will this program run is determined by the command line argument n. What computation is happening, you don't need to care about, okay? And I would like you to believe that I have faithfully written an equivalent C++ program as well, and instead of structures it uses Java simply, it uses classes simply, and a Java program as well. All of the programs are supposed to do the same computation with minimal differences among the way they are written, okay, just the syntactic sugar of that particular language, all right. So there are 3 nested loops, and this is a common computation. You do matrix multiplication, you do a lot of stuff where you have nested for loops. It's representative of a lot of computation that we do, okay. And I have a script now, a shell script that just compiles and runs all those programs, and while running it I am printing the amount of time it takes. Of course, the number of iterations has been taken as a command line argument. I will just run it now and we will see what happens. Since all of you agreed that Java is supposed to be a slow language, we will see some magic here. Okay, so I will run the loop for, let us say, to begin with 100 times. So, I have 100 times, 100 times 100, 3 loops are running each 100 times, right. So, they are nested and we will get the times taken by each of the programs. As expected, Java seems to be slow, but do you really care whether it takes 0.067 seconds and so on. So, let us make it run longer. Okay. Let us make each loop run 500 times now. Java, okay, maybe an aberration, maybe it is just a one off occurrence. Let me make it 1000. So, the first is for C, second for C++, third for Java, same programs. Okay. All right. Now, it looks exciting. Who said Java is slow? I didn't, I asked you. I will ask this question at the end and then you should answer it in a better way. Okay, 1500, 7, a lot of time. What is happening in this talk? Just waiting. But Java did not let you wait at all, right? So I mean the point here is that Java is no longer the slowest of the lot. It can sometimes be even faster than the ones which we used to consider fast for the last several decades and so on. Okay. So, that is where with that point in mind, let me ask you another question. Are Java programs interpreted or compiled? Now, those of you who know compilers, you can answer the question at least. Interpreted, raise your hand. Java programs, are they interpreted? Okay, I see few hands. You are right actually. Are Java programs compiled? Okay, more hands. You are also right. Right. So, Java programs are interpreted as well as compiled. Are programs that are executed post compilation supposed to run faster, or interpretation of programs should be faster? Compile, right. All of you know that compilation optimizes the program and the generated binary is expected to run much faster than an interpretation of a plain program, right. So, the thing is Java bytecodes, first of all you get Java bytecodes when you compile Java using Java C. So, first of all they are compiled, and then what do you do with bytecode? You hand it over to the Java virtual machine, right. It is not just specific to Java, C# is translated the same way, many versions of R, Python, many other languages are translated the same way. Okay. So, sometimes you get some machine independent bytecode and then you give it to some beast that makes it run very fast in this case, right. So, the way Java programs are compiled and executed can be summarized like this. You give some Java files as input to the static Java compiler on a certain machine, you get bytecodes. For each class in this file you would get a dot class file which contains the platform independent bytecode that all of you might have heard about, and then those bytecodes are executed on the Java virtual machine. The Java virtual machine, of course, since it is platform independent, you can run these bytecodes on any machine where you have installed the JVM for that machine, right. And then on the JVM, to answer the question of the previous slide, Java bytecode can be interpreted by this interpreter, or they can be compiled and then executed by one of these compilers as well. Okay. So, JVMs contain both an interpreter and one or more compilers, all right, and that is what gives you the speed. So, we will see how does it happen, we will get a glimpse of it in today's talk. And these compilers, since they exist in a machine that is executing your code, that is executing Java bytecode, it's happening when you are already interpreting the program. These compilers are called just in time compilers. They are compiling the program just when they feel it's required to do so. Okay. So, let me explain to you a bit the notion where you have interpreter and compiler residing in the same execution environment. It's usually called tiered interpretation and compilation. Okay. There are multiple tiers. So, in the Java virtual machine that you use on most of your machines, which company produces it? Oracle, right. So, Oracle's hotspot Java virtual machine, once you run your Java bytecode using the JVM, it may be in one of these states. It may be either being interpreted or there may be 4 levels of compilers which may be compiling your code. Okay. So, the JVM is not a simple, just a GCC compiler has just one compiler. Here you may have multiple compilers with different levels of compilation as well as an interpreter living in the same virtual machine. Okay. So, let me just show this to you in a demo again. So, we said that the Java program here ran very fast, we saw it. Now, so here you could see, so I am just printing how did the compilation work out while I was running this program test for using my JVM. So, as you can see, I told you 0, 1, 2, 3, 4 something, right, different levels of compilation and interpretation. So, here it shows you that somewhere in the method foo, which is doing the main for loop computation, you are compiling that method at level 3, then sometime you are compiling the same method at level 4, then again level 3, 4 and so on. Okay. So, you can see that see it happening, at least, that when I said a program can be or a part of your program, in this case the method foo could either be getting interpreted, it may be compiled at one of the levels and so on. So, you can see it happening as well using this flag. Okay. So, it is indeed happening. So, your Java bytecode is not just getting interpreted, it is also getting compiled by one of these just in time compilers, level 3 or level 4 compilers, and hence you get that performance that you were able to see. Okay. So, that is one thing to note down from here. We will come back to this slide later on, okay, or this figure later, this image later on. Any questions at this stage? Yes, yes. So, they do correspond to the amount of optimization that happens. You can say that level 4 optimizes more than level 3, strictly speaking. Okay. Good question. Anything else? Let us move on. So, let us see how does JIT compilation happen in the hotspot JVM. So, what happens is, what is the first method that is executed in Java programs? The main method, right. So, you start interpreting with the main method, okay, and you know about this 80-20 rule, I am sure, where you say that 80% of the execution time usually is spent in 20% region of the code. Well, 80-20, 90-10, 85-15, whatever may happen in a particular program, but there are certain regions in your program that are supposed to be executed frequently and they consume more amount of time in getting executed. So, the idea is you start interpreting, okay, then you identify which regions of your program are hot. That is how the name hotspot JVM came as such. So, which regions of your program are hot enough to deserve compilation, to deserve just in time compilation, alright. So, you start running the program by giving it off into the interpreter from the main method, and you keep doing some profiling, you keep finding how many times a method is called, how many times, okay, can somebody tell me what should a back edge represent in a program, in a control flow graph per se? Sorry, loop, right? Yeah. So, if you have back edges, that means you are traversing over a loop. So, if you count the number of times a particular back edge is executed or taken, or if you count the number of times a method is called, it gives you an idea of the regions of your code that are hot, that are executed frequently. Is that okay? So, now I started with the interpreter, I start counting, I also additionally keep counting how many times a method and a loop is getting executed, and then as I find those regions that are getting executed frequently, I insert them into a compilation queue. Okay. So, why queue, we will come back to this question, but there is a compiler thread running in the background waiting for methods to compile, and then the JVM will hand over these hot methods or hot loops to the particular queue of a particular compiler, level 1, 2, 3, 4, any of the compilers, alright. And then the compiler will compile those methods, it will keep picking the head of the queue and start compiling that method. In the meanwhile, your program is not pausing. So, JVM is a very multi-threaded process, okay. Your program is not pausing to wait for the compiler's output, you continue with interpretation. Let us say in the previous example, you compiled the method foo, now the next time foo is called, if the compiler has already produced a binary, an optimized binary of the method foo, then you will no longer interpret foo, you will switch over to the binary version of foo, the compiled version of foo, and then you will start executing from over there. Is that clear? So, that is how the tiered compilation works in the JVM. So, entry point, if you just one second. So, if you see, when I said you are calling foo at some places in the program, you are interpreting foo, and next time you see a call to foo, you no longer want to hand over to the interpreter, you have to go to the compiled version of foo. So, if you see the entry point, the address at which you enter or start executing foo has to change. Okay? So, while your program is running for a particular piece of your code, the place at which the execution has to start, or whenever you see a call to that piece of code, the address to which that call is linked has to change dynamically. Okay? This is called this, and similarly if a loop is getting executed inside a method, the loop has, you iterated let us say 5000 times, now the compiled code is ready, the 5001th time you iterate over that loop, you want to hand over to the compiled version. So, you basically go from the interpreter world, so JVM interprets in a stack machine, go from the stack world to the native world of your machine, whether it is an Intel machine or AMD machine or PowerPC and so on, and this process, when you move from one place to another, you change the addresses dynamically while your method is on the runtime stack. This process is called on stack replacement. Okay. Digest it till then I will take a question. You are getting a mic, just one second.
So, yes sir, so the question is like we don't know how many times a function will be called. So, how will we be deciding whether when to switch from interpreter to compiler?
Well, that is a good question again. So, what is your name? Siddharth. Okay. So, Siddharth asks, how do we know whether compiling a code is going to be beneficial? Well, let us say I started counting and I have put a threshold that once a method is called 10,000 times, I will give it to the I will insert it into the compiler's queue. But is there a guarantee it will be called 10,000 times more? Maybe 10,000th was the last time. Then it is sorry state, you have spent a wasteful effort in compilation. Okay. So, it is a heuristic based technique in general. If the guess is that okay, it has been running for really long time, so let me give it a shot by compiling it, and then probably it will run for even longer. Well, it is not such a bad state because there you have multiple levels and so on. So, you can keep different thresholds for different level of compiler, as you could probably guess, and that partly answers your question, right. Okay. Any other question? Yes. What is your name? Please tell your name and then answer, and then ask.
Yes sir, my name is Harsha. So here the speed up is happening because we are moving from to the compiled code.
Exactly.
Then in that case, completely compiled code should be faster, right?
Yes, completely compiled code should be faster, but I will take the same point. If the code is compiled and it is never executed again, you spent extra resources in compiling the code, isn't it? So, that extra amount is saved if you do tiered operation instead of directly compiling everything in the VM. Okay. But I will take Harsha's point and contrast it to the way static compilers work like GCC, where you actually compile the code in the beginning and then hand over a binary, versus this where you are doing JIT compilation in a VM. We will come back to it just in a couple of slides. You will see what all we can do additionally in this kind of a mode compared to static compilation. Okay. Shall we go ahead? So, there is a food for thought for you. Maybe just try to think what all you have to do in terms of the runtime. How do you have to update the program counters? How do you have to update the values of the registers and so on when you do on stack replacement? You are going from one environment to another for executing a certain piece of code. You would have computed some intermediate values. You are doing sum plus equal to I in a for loop. Half of it you did while you were in the interpreter. Now you are going to the native world of your machine to run the compiled code. What all operations will have to be done? It is a very interesting engineering that happens in JIT compilers for performing on stack replacement. All right. Okay. So, now when I had said we have multiple levels of a compiler, you see here somewhere, right, interpreter with some profiling, C1 compiler, then C1 with invocation and backage counting. Now you know what was this counting going on. So, you can differentiate level 1 with level 2 here. Both are the same compiler, same amount of optimization, but in the level 2 you are also doing some counting, you are also doing some profiling. Okay. Now, what is left is this gray phrase with full profiling. Okay. So, the point over here is, if I could count the number of times a method is called, if I could count the number of times a loop is executed, that is helpful for me to decide when to switch over to compiled code, isn't it? Why not count more things? And that would answer Harsha's question partly. Why not count even more interesting things? So, what could be more interesting things that you can count while running the program? Just counting, counting or storing in some data structure, similar operations, simple operations, right. So, if I give you a hint by saying, if you profile more things than just the count of times a particular code region is executed, you may be able to do speculation. Speculate means guess, make a guess what is going to happen. Can you give some examples? What additional things can I count while running a program that might allow me to optimize more? Yes. Okay, that's a good point. I don't think any JIT compiler does it though till now. So maybe that's a good thing to try out. So he is saying that we can count how many times a particular object is accessed. Well, the hardware will make sure it's already in the cache when you are accessing it frequently, but maybe you want to force it to live in the cache if you know that it's probably going to be accessed again. Okay, that's one good example. Anything else? Yes. Okay, if you count the number of variables created, what will you do with it? Okay, okay. Well, now if you can know how much amount of memory it's going to take, but I would argue that you can do it statically by looking at the program and upper bound over the number of variables. You could still do it statically, right? So that's a fine point, but we are thinking about things that would benefit us more by doing it at runtime while running the program. All right. So let me show you a few more examples over here. Basically, the JVM does perform a lot of or several speculative optimization. It does a lot of speculation. It tries to predict which branch will be taken. It tries to remove null checks in your code. If you write Java programs, your programs have implicit null checks whenever you dereference a variable. And then you have polymorphic calls, virtual calls. They are supposed to be expensive. Can I resolve them to a single method? Can I make a polymorphic call monomorphic? Can I inline a method? Function inlining is said to be the mother of all optimizations, right? So, can I inline methods based on runtime profile? Can I do newer optimizations that a static compiler cannot even think of doing, and so on, okay? So, that is the idea about speculative optimizations. Let us have a look at an example. So, let us say I have a piece of code here, method foo, that takes two arguments. One is an integer, one is of some type x. It adds 10 to the first argument, and then in between it calls the method bar by dereferencing the variable o, the reference variable o. Okay. This is a polymorphic call, right? If you have implementations, 3 implementations of bar, let us say x is extended by y is a child of x, z is extended by y. There are 3 bars in each of the classes x, y and z that do different things, that perform different computation. So, can you tell me how many bars can be called at this place? It is a virtual call, right. So, which all bars can be called at that place? Can it always be x classes bar, or can it also be y classes bar and z classes bar? It depends on, so you might have heard of this term, right. The method that is called at runtime in O languages is determined based on the runtime type of the object pointed to by the receiver variable. In this case, whether O is pointing to a x type object at runtime or a y type object at runtime or a z type object at runtime will determine which bar is called at runtime. Is that clear? If it is not clear, just ask, otherwise you will not get the remaining of it. Is that point clear? Any of the bars can be called here based on what actual object is pointed to by the variable O. Is that fine? Okay, I see some nods. Alright, so this is a polymorphic call. Now let us say I am interpreting this program, or I am compiling it in that level 2 where I am allowed to do some profiling and so on. What if I also find out, what if I also record, what if I also profile things about the arguments taken by foo? What if I let us say I find that whenever I am calling foo, or the last 10,000 times I am entering foo, the value of a was 10. It was always a constant 10. It is not a constant as per the program, so I cannot determine this statically, but while running the program, let us say I find that every time a is just 10. What can I do? I can perform constant propagation. I can remove the variable a. I can, instead of doing c is equal to b times o dot bar, I can directly propagate 10 plus 10 and make it 20. Is that clear? All of you know this optimization. Constant propagation can be done with the assumption that a is always 10. Let us now make an assumption on the second argument as well. Let us say the last some k number of times I entered bar, the type of the object pointed to by the variable O was always y. If it was always y, can I inline the bar which was defined in class y? That is the question over here, right. So, if I inline under this assumption, if I inline y dot bar, then I can just assume that it is going to return 2. I can say 20 times 2 over here instead of making a method call. A method call is very expensive. You have to switch over from one activation record to another, you have to create that one, you have to transfer variables, you have to store the return address, so many things have to be done. Okay. So, you avoided function call, you inlined the effect here. Can you suggest any more optimization that can be done here now? Again I can do constant propagation over here and I can say return 40. So, now just think, the original version of method foo had an addition operation, few variable loads, multiplication, method call and then a return. Here I just have return 40, that is it. Is this foo supposed to be faster than the original foo? Yes. Would I be able to perform it in a static compiler? No, I do not know the value of A, I do not know the type of B. Okay. But a JIT compiler would be able to speculate based on the same. Yes. Oh, okay. Yeah, I started at 2:38. I will take 5 minutes. Okay, all right. I'll try to finish quick. Okay, so now you have obtained a more, you have obtained a faster version of foo, less memory occupying version of foo, and then you can dispatch to this version of foo. You can just compile it, get a binary. Whenever I call foo, I will not interpret this foo, I will not perform this method call and so on. I'll directly dispatch to this binary. All right? Yes. Yeah, of course, those are standard optimizations, like some multiplication can be reduced by a shift of bits and so on. Those things can essentially be done. Yes, that is very good. Yes. Very good, very good. So, what is your name? Ayushi asks, we made an assumption and compiled the code under assumption. How do I take care that the assumption holds true? How do I record it and how do I make sure that the assumption holds true? Okay. So, in the JIT world, this is called a guard. This binary is valid under the guard that A's value is 10 and O is pointing to an object of type Y. Okay. So, there is a guard put over here, and whenever you enter this binary can be executed only if the guard evaluates to true. Is that fine? So, this guard is something you additionally store here, but under that guard you can perform several optimizations inside foo. Okay. But let us say I had put this guard, what if the assumption enclosed in the guard fails in a subsequent run? Next time I call foo and I pass 20 as the first argument instead of 10. Can I continue using this binary now? No, that binary is invalid, that binary will do something wrong, it may fire a missile, you do not know what all it can do. Okay. So, the idea is in JIT compilers you perform speculation, but then at some points the assumptions that you made may go wrong, and at that time you have to de-optimize your code. Okay. So, you have to fall back to another path. So, let us say I found a call to foo where the guard fails. Where could I go now? I could safely go back to interpreting the original code again. Okay. I should still maintain the original byte code, I can start interpreting the byte code. Okay. So, that is called de-optimization. You optimize, now you are undoing the effects of optimization. Okay. So, well, we could see, in fact, you saw here that sometimes you had this remark made not entrant. So, there was a code where you could enter, now you have made it not entrant, you can no longer enter that piece of code in future. So, there could be multiple states, your code could either be made not entrant, it could be a zombie code so that a garbage collector can collect it out and so on. These are standard terms, compilers people are not so boring. Okay. Alright, so we do a lot of research in this space. So, I have just introduced you to the world of JIT compilers, the kind of optimizations they can do and so on, and there are several interesting things. Nobody asked me in the example that I showed, what if I ran or compiled the C program with -03, will Java still beat it? Probably no, because there are some optimizations that GCC can perform, but Java compilers cannot perform. Why? All these optimizations are happening when you are running your code. So, you are very time constrained, isn't it? You can't spend too much time in compilation. So, it is a very exciting direction being pursued by our group, that is trying to find how can we make the analysis performed by JIT compilers more precise without increasing the time required to perform the analysis. Okay. How can we reduce the cost and frequency of de-optimization? It looked like a waste of effort, right? How can we reduce it? Yes. Well, LLVM is not a runtime VM. So, you do not know values of variables while you are compiling code in LLVM, is not it? That is also a static compiler. Yes.
So, what was the optimization level at Java?
That is a good question, right? If somebody says I can put -03 for GCC, I can put something for Java as well. Right now everything was default in my shell script, no optimization levels for anything. Okay? So, well, Java need not be fast sometimes, but you can do interesting things. So, okay, before I finish, I am about to finish. Question of the symposium: which programs are the fastest? If you say Python, you should not study. Anything else? Well, it's not true actually. It's not true. I'll disprove myself. Okay, so the answer is no programs are fast or faster, no language is fast or faster. It's the compiler that makes them fast, and that's what we work on. Okay, so here we have this research group called Compel, Compilers and Programming Languages at IIT Bombay. We perform many of the interesting optimizations. We try to introduce new optimizations related to speculation. We have been trying to reduce the cost of de-optimization. We have been trying to do it for Java, for R, for Python, for many other programming languages as well. Okay. So, and one interesting thing is most of the work that we are doing is getting implemented directly in industry compilers in collaboration with people who are developing those compilers. So, it is very exciting to work on these. It is a learning opportunity for everyone. Okay. So, if you want to join our group, please do so. Thank you.
Let's thank our speaker once again for this wonderful talk.